Hold on here. Okay, can you see the slides? About the slides? Okay, good. All right, we stopped yesterday, right? We stopped here yesterday. We talked about formation of ohmic contact and Schottky contact. Okay, so we already have the guidance here, the table that you can use in order to decide whether it's going to be an ohmic contact or a Schottky contact. Okay, so let me just recap, what you have to look at is two things. First is the work function of the material, work function of the metal versus semiconductor. Second thing is either the wafer is p-type, the semiconductor is p-type or n-type. Okay? So for the case where the work function of the metal is more than the semiconductor, okay, so and if your semiconductor or your silicon in this case is n-type, then you're going to have a rectifying contact in your device, or Schottky contact. Okay, Schottky contact. On the other hand, if your work function of the metal is less than the semiconductor, and you're working on n-type silicon as well, you're going to have an ohmic contact. Okay, so we're going to go through the properties of these two contacts today. So this means if you're about to work on a semiconductor device, which requires you to produce ohmic contact or Schottky contact, you can actually design the junction, okay, by knowing whether your semiconductor is p-type or n-type and pair it accordingly with the right work function metals. Okay, so you can do that. So we have a list of metal contacts that can be used in order to form the metal semiconductor junction with a range of different work functions. You can see here. Okay, if you search this on Google, you can even see a spectrum, a plot of this list in increasing work function or decreasing work function for you to choose. And then we also have to know the electron affinity of our semiconductor material, because we need to draw the band diagram. Okay, the band diagram of the junction. So metal semiconductor junction or interface is also a form of a junction. So junction is not necessarily a PN or PIN, but it can also be between metal and semiconductor. So let's look at the first case. What is the first case? Okay, let's go back to the table. The first case is about Schottky contact or rectifying contact. So in order for you to have this, then, so in this case, let's have a look at the diagram first. The silicon is n-type. Okay, the silicon is n-type. So we're now talking about this column. Silicon is n-type. For you to have Schottky contact or rectifying contact, kita nak pakai apa? Work function has to be bigger than or smaller than the semiconductor work function. N-type silicon. Schottky contact, bigger than, right? Good. So bigger than. So the work function of the metal has to be bigger than the silicon in this case, since we're working on n-type silicon, for us to have a rectifying contact or ohmic contact or Schottky contact, sorry. So now let's look at this. So now you are about to combine two different materials. First one is your metal, second one is your semiconductor, and the diagram for A, the top one, is before joining both materials together. So we know that we know the band diagram of this metal, for example, and we already know the band diagram of this silicon, for example, and then this is how they look like before they join together, the band diagram, okay? And the diagram in B is when they join together already. Okay? When they join together. So now let's look at this. Before joining, okay, we know that the Fermi energy of the metal looks like that when we learned about the Fermi energy back then. Okay, so it is like this. And then we also have the Fermi level of the silicon on the right hand side. So Fermi level is close to conduction band since the silicon is n-type, right? So remember the tables now. And in this case, in order for us to have a Schottky contact, we talk about the work function of the metal has to be bigger than, right? So bigger than. Look at this. Q phi m times Q phi s. Sebab kita kena convert lah. Kalau nak, if you want to convert into energy, then you have to times the electronic charge. So this is the energy axis, if you like. This one is the space axis. So now the phi m is bigger than phi s. Okay. So with respect to vacuum level, E naught, okay? Kat atas, vacuum level. So the rest is still the same. You still have to draw the Fermi energy for the metal, and then the EC for semiconductor, EV for semiconductor, EI for semiconductor, the intrinsic level. And then you have to label everything accordingly, right? Label the phi m, phi s, and then label the electron affinity, which is the distance from EC to the vacuum level. Electron affinity times electron charge in order for you to get the energy to go on the energy axis. And then this is how they look like when they combine. Okay, let's go through. So don't kita tengok the description there. So we're going to have phi b naught on the left hand side, the barrier height on the left hand side. We also have the barrier height on the right hand side, just like the way we had PN junction last time, remember? Remember QVBI? And then the what you call the phi n on the right hand side, and then the depletion width as well. So we do have depletion region for metal semiconductor junction as well. So before the contact, the Fermi level in the semiconductor was that above in the metal. So you can know this by starting to draw the phi m versus phi s, and then the rest will fall accordingly, right? So in order for the Fermi level to become a constant through thermal equilibrium, remember last time, the moment we have thermal equilibrium, we're going to have a single chemical potential or a single EF in the system, okay? So now the system is about metal semiconductor junction. So we're going to end up with this, a single EF in the system, and electrons from the semiconductor flow into the lower energy states in the metal. Okay, how does this happen? Electrons from the semiconductor. Okay, bila you tengok this statement, look into the first band diagram. Okay, the moment you have drawn this completely ready for the band diagram before the contact, which EF is higher, EF of the metal or EF of the semiconductor? Which EF has higher energy than the other EF? Look at diagram A. Metal or semiconductor is higher? Okay, you want to say metal? Okay, obvious, right? Kalau you boleh draw this one correctly, then you can see clearly that the EF is higher. So since the EF is higher in the semiconductor, electrons from semiconductor are going to flow into lower energy states in the metal. Okay. Upon the combination of both metal and semiconductor, bila you join, just the way we discussed with our PN junction last time, remember? So when you have a P side, N side combined together, you're going to have diffusion gradient, concentration gradient, and then the holes on the P side is going to diffuse into the N side, electrons from the N side are going to diffuse into the P side. And the same is also applicable for the metal semiconductor junction here, where the electrons are going to flow into the lower energy states. As a result, positively charged donor atoms remain in the semiconductor, creating a space charge region, SCR. So we're going to have SCR, which is formed in the semiconductor region, forming the depletion region, SCR or depletion region. Huh? We normally label this as W. So the parameter phi B naught here on the left is the ideal barrier height in the semiconductor contact. That is the potential barrier seen by electrons in the metal. Okay, so note that we have two barrier heights here. Two barrier heights. Satu dekat kiri, left hand side, in the metal, seen by carriers in the metal for them to cross. And another barrier height is the barrier height in the semiconductor, QVBI, seen by the carriers in the semiconductor, preventing them to flow. Macam barrier, you ada wall kat sini, stopping them to flow, and you have another wall on the left, stopping them to flow as well. So remember, we have two barrier heights, not a single barrier height. So this phi B naught is the potential barrier seen by electrons in the metal, stopping them to flow. So this barrier height is known as the Schottky barrier. So this is what we call as Schottky barrier, due to the formation of Schottky contact. And it's given by the phi m minus electron affinity. You can go back to the diagram. Okay, diagram dah ada ni label, everything. On the semiconductor side, so the first one is on the metal side, metal. So this one is semiconductor side block. So the VBI is the built-in potential that we discussed last time during the PN junction. So this barrier, similar to the case of PN junction, is the barrier seen by electrons in the conduction band. Okay, so now that this barrier on the right is seen by the electrons in the conduction band, preventing them to flow into the metal. Okay, and this potential barrier is given by phi B naught minus phi n. Okay, phi B naught on the left minus this guy, phi n. So which makes VBI a slight function of semiconductor doping, as in the case of PN junction. So since it's depending on the semiconductor, VBI depends on the semiconductor doping. So let's recap. How does VBI related to the semiconductor doping? VBI, how is it related to semiconductor doping? Na or Nd? Say Na. Oh no, Nd lah sebab ni N-type kan, silicon. What is the relationship between VBI and Nd? Anyone? From our previous topic in PN junction? Remember the VBI equation? What does it say? How is it related? Are they proportional to each other or are they reciprocal to each other? Anyone can recall? VBI equals to? Remember when we did the calculation last time? 0.947 VBI equals to what? Ln apa? VT ln, right? Isn't it? VT ln something, right? Anyone can recall? Rafai? How are they related? Proportional or reciprocal? Oops. Proportional or reciprocal? Paris? Okay, Maria said ln ND, okay, hold on. Proportional to ln ND, a question. VBI to potential barrier. Yes, VBI is a potential barrier in the semiconductor seen by electrons in the conduction band. Nih yang sini nih. If you look at this curve again, this is band diagram ni kat sini. Before this, we've been talking about a single VBI, right, in PN junction, and this is two potential barrier, and VBI is in the semiconductor side. So proportional to ln ND, yes, it is. Betul. Apa Joanna? Can you remember the equation? VT ln NA ND over NS squared, right? Joanna, betul ke? Betul kan? So VT ln NA ND over NS squared. So VBI is then proportional to the doping level. Okay, go back and see the equation. All right, so this is the story behind this formation and everything, including the bias that if you apply the bias. Okay, yang tadi kita tengok the band diagram is under thermal equilibrium. Remember thermal equilibrium of metal semiconductor junction, TE. So the same thing that we did for our PN junction, we can also apply forward bias or reverse bias to our metal semiconductor junction as well. Okay, so in this on this page, diagram A is about reverse bias ke forward bias? Using your knowledge in PN junction. Reverse kan? Tak ada kan caption kat bawah tu. So here is the reverse bias plus VR. You can see the very height increasing. And then the diagram B is about forward bias, the very height reducing. Nampak minus VA plus VA. Ini very height is getting bigger. And this one is getting smaller. Okay, due to the application of the bias on the junction. Okay, if you want to imagine this physically, let me just draw for you to imagine. Katalah you have an N-type silicon and silicon. So what we are doing now is we are putting a contact, a metal contact. Okay, that's all. Done. Okay, and we know that the metal contact work function is bigger than the work function of our semiconductor material as given on our previous page. And now what we're doing on this page is just to apply a bias. So either forward or reverse bias, okay? So if you're talking about reverse bias, then okay, let's see. If you apply a bias, a positive voltage, okay, if you apply a positive voltage on the semiconductor with respect to the metal, so now we're talking about positive voltage on the semiconductor. Besar sikit, let me just exaggerate. With respect to semiconductor, the metal to metal barrier height increases, semiconductor to metal barrier height increases, while phi B naught remains constant in this case, and this is called reverse bias condition. Okay, so if you apply like this, the positive voltage is called a reverse bias condition. Does it make sense? In terms of the circuit connection there? For reverse bias, look at the polarity. Does it make sense? If you can relate back to the no, you said no. Positive voltage to N-type. Does it make sense? Positive voltage to N-type, forward bias or reverse bias? Just like what we discussed in our PN junction biasing last time, bias condition. If we connect, reverse bias, right? So this is reverse bias, isn't it? Betul, Julia? Okay, if you connect N-type to positive, it's reverse, isn't it? If you connect N-type to negative, forward bias. So in this case, it's reverse bias. So saya draw tepi tu bukan, I'm not drawing for the forward bias, I'm drawing just because I have space there. Okay, ini bukan saya draw untuk forward, I'm drawing for reverse bias. To illustrate reverse bias. So if a positive voltage is applied to the metal with respect to semiconductor, if positive voltage is applied to the metal okay, at the same time, okay, this is still positive voltage. The semiconductor to metal barrier is reduced. VBI is reduced at the same time, while phi B naught against remain essentially constant. If you can notice here, these two remain constant. So in this case, electrons can flow more easily from semiconductor into the metal since the barrier has been reduced. Electrons can flow more easily from semiconductor into the metal. So when you discuss about the flow of electrons, you have to look at what is changed. Is it the barrier on the metal side or on the semiconductor side? So in this case, if the barrier for the semiconductor is reduced, if you apply forward biasing, okay, okay, this is called forward condition. If you apply forward bias condition, then the barrier will be reduced. Then the flow from the flow of electrons from semiconductor into metal can take place again. So this is the two conditions. VR is the reverse bias and VA is the forward bias. Right. IV characteristics are similar to PN junction diode, energy band diagrams. For IV curve, due to flow of majority carriers, the mechanism is the flow of majority carriers. So in forward bias, the barrier seen by electrons in semiconductor is reduced. If you do forward biasing, the VBI is reduced in the semiconductor side. Okay, so the majority electrons from the semiconductor can flow into the metal. Okay, so the EF is to begin with is higher than the EF in metal. The forward bias current is in the direction from metal to semiconductor, right? Due to the flow, tadi kita tengok direction ya. Okay, metal is on the left, semiconductor on the right. If I can just draw an imaginary junction interface here, metal belah sini, semiconductor belah sini. So due to the forward bias, electrons flow from left to right. Sorry, left to right. Right to left, sorry, right to left. Semiconductor to metal. As a result, we're going to get an opposite forward bias current from metal to semiconductor. I forward bias is going to flow this way on the opposite direction of the electron flow. Okay, exponential function of the forward bias voltage, just like the IV Schottky curve. Okay. So on the other hand, if you talk about ohmic contact, let me just go through for another few more minutes. Ohmic contact. It's called a non-rectifying because it allows the current to flow into both directions, two directions. Ohmic contact is a low resistance junction. Okay, the first one is high resistance. Schottky is high resistance. Ohmic is low resistance, providing conduction of both directions. Non-rectifying nature between metal and semiconductor. So current through the ohmic contact is a linear function of the applied voltage, as can be seen here. And the applied voltage should be very small. We have two types of ohmic contact. The first one is ideal non-rectifying barrier. This is the one. And the second type is called tunneling barrier. We're going to see tunneling later on at the end of this topic. Tunneling barrier. So both are ohmic in nature. So this is the case for ohmic. So if you look at this, first thing is look at the in this case, look at the EF. Okay, EF of metal is now higher than semiconductor. Just now when we talk about Schottky is on the opposite direction. And so EF here, EF for silicon is close to EC, so it's N-type. So look at the work function now. The work function of the semiconductor is bigger than, or metal is smaller than semiconductor and N-type. Go back to this table. metal is smaller than and is n-type. So we are now talking about this case. Tadi first case kita discuss tentang ni. Sekarang kita discuss tentang ohmic, right? And for this and this, it's just the reverse case. Okay? Reverse sama aja. Same thing. So we've considered an ideal metal n-type semiconductor in our previous case. So now figure 9.11 is the one that we're talking about now, before contact on the left and after contact on the right at thermal equilibrium. Okay. So the work function of the metal is less than, you can see there on the left hand side. So before the contact, okay, to achieve thermal equilibrium in this junction, electrons flow from the metal into the lower energy states in semiconductor. So why is it happening? Why electrons are flowing from metal into semiconductor in this case? Anyone? Why do we have electrons flowing from metal into semiconductor? Look at the left band diagram. Kenapa electron flowing from metal into semiconductor? Why? Nak beres. Okay, let me just finish off this slide and then we're done. Okay, anyone? Anyone? Why is it flowing from left to right? Metal into semiconductor. Metal kiri, semiconductor kanan, left and right. Why is it the case? Okay, let me. Because the metal energy is lower. What do you mean? Metal energy, Juwaria? Lower Fermi energy. Which one is lower, Cornelia? Which one is lower than the other one? Be more specific. Which one is lower? Which one has lower than which one? What causes the electrons to flow from metal into semiconductor? Which one? Okay, so good. So bila kita nak tahu, when you want to know the direction of electrons flow, you have to look at which one has higher EF. So in this case, the EF of metal is higher than the semiconductor. So remember last time when we talked about the definition of EF, the probability of finding there, right? You can see more electrons there. So bila electrons ada lebih banyak di metal, then we should expect metal electrons to flow from the metal to the semiconductor. Because the energy level of the EF is in the metal is higher than this EF. Okay, case number one tadi, ohmic. Look at the energy. EF of semiconductor is higher than the metal. So that's why the electrons flowing from atas ke bawah. So dia macam flowing downhill, flowing downhill. Right? So in this case, in our new case, ohmic, electrons are flowing downhill from, but downhill tu maksudnya higher energy level to lower energy level lah. So dia akan flow from metals into semiconductor. So excess electrons charge and the n-type is actually a surface charge density. So you're going to have surface charge region. Then if you do the biasing, if a positive voltage is applied to the metal, there's no, you always need to draw this in order to comprehend better. N silicon, then metal, then you do the biasing. Okay. So if a positive voltage is applied to the metal positive voltage applied to the metal, there's no barrier height, electrons flowing. Yeah, so electron akan flow into the semiconductor into the metal. Look at the band diagram here. Okay, phi Bn on the left, phi n on the right, and the rest remains the same, single EF. And you should be able to draw the rest as well. So if positive voltage is applied to the semiconductor, the effective very high. So when you want to discuss the flow of the carriers from either side, you need to look at on which material, metal or semiconductor, is the bias applied. Okay, Positive connective, you have to look into the direction of the bias punya material. They apply on metal or semiconductor. So if positive voltage is applied to the semiconductor, the effective very high for electrons flowing from the metal into the semiconductor will be approximately equal, no change. Okay, fairly small for moderate doped semiconductor. For this bias condition, electrons can flow easily from metal into semiconductor. Nanti kita akan let me just go through this again. What is tomorrow? Tomorrow is Thursday. Today is Thursday. Alamak, tomorrow dah Friday dah. It's okay. So we just stop here first. I'm gonna come back to this ohmic connection punya mechanism next week, and inshallah next week we're gonna finish the rest of the metal semiconductor junction, and then we're gonna talk a little bit about tunneling, and then we're gonna move on to semiconductor heterojunction. So we've been discussing about semiconductor homojunction, same material, same band gap. Then we're gonna talk about a semiconductor heterojunction. Okay, for example, if you talk about crystalline silicon or amorphous silicon or zinc oxide or cadmium telluride or some opposite materials or different materials entirely. Okay, so we're going to come back to that after we finished with the semiconductor metal junction. Is it okay so far? I'm going to come back to the ohmic connection next week, next Monday, inshallah. Okay, is it okay? All good? Right then, I'll see you next week. Bye-bye. Assalamualaikum. Take care.